Welcome back! In the last lesson, we built two parallel simple clippers. The diode set in parallel with the output, and when it turned on, it pulls the output to 0. But the clipping level was always exactly 0 volts. Today, we keep the same parallel topology, but we add a DC battery in series with the diode inside the shunt branch. This battery moves the clipping level away from 0. When the diode turns on now, the output does not go to 0. It locks at the battery voltage, plus V or minus V. The parallel biased clipper acts like a voltage limiter. It lets the signal pass until it reaches a threshold, and then it clamps the output at that threshold. We have two choices again: the diode orientation, positive or negative, and the battery direction, 1 or 2. 2 times 2 gives 4 parallel biased clippers. The method is the same as before. At the switching instant, the current I is 0 and the diode voltage Vd is 0. Apply Kirchhoff's voltage law around the shunt branch. With I equal to 0, there is no voltage drop across the series resistor R, so Vo equals Vi at the transition point. In the shunt branch, with Vd equal to 0, Vo equals plus V or minus V depending on the battery direction. That gives the transition voltage. Direction 1 places the transition at plus V. Direction 2 places it at minus V. Once you know the transition voltage, the rule is simple. On one side of the transition, the diode is on, and Vo is locked at the battery voltage. On the other side, the diode is off, no current flows through the shunt branch, and Vo equals Vi. Variation 9. Positive, parallel, biased, direction 1. The diode is in the same orientation as the positive parallel simple clipper. The battery sits in series with it in the shunt branch, direction 1. The transition voltage is plus V plus 3 volts. When the I is above plus 3 volts, the diode turns on. The shunt branch conducts and the output locks at plus 3 volts. The positive peak of the sign, which would normally reach plus 10, is clipped flat at plus 3. When the I is below plus 3 volts, the diode is off. No current in the shunt branch, so Vo equals Vi. The output follows the input for the entire lower region. The result looks like the full sine wave, but with the positive peak sliced off at plus 3 volts. The battery set the ceiling. Variation 10. Negative, parallel, biased, direction 2. Now the diode is in the negative orientation, and the battery is in direction 2. The transition voltage moves to minus V, minus 3 volts. When Vi drops below minus 3 volts, the diode turns on and the output locks at minus 3 volts. The negative peak, which would reach minus 10, is clipped flat at minus 3. When Vi is above minus 3, the diode is off and Vo equals Vi. The output is the full sine wave with the negative peak sliced off at minus 3 volts. Variation 10 is the mirror of variation 9. One clips the top, the other clips the bottom. Variation 11. Positive, parallel, biased, direction 2. Same positive diode orientation as variation 9, but the battery is now in direction 2. Direction 2 moves the transition to minus V, minus 3 volts. When Vi drops below minus 3, the diode turns on and locks the output at minus 3 volts. When Vi is above minus 3, the diode is off and Vo equals Vi. The output waveform is the same shape as variation 10. Only the internal wiring changed, the diode and battery arrangement, but the clipping result is the same. The negative peak is removed at minus 3 volts. This shows that different circuit configurations can produce identical output waveforms. Variation 12. Negative, parallel, biased, direction 1. Negative diode orientation, battery direction 1. The transition voltage is plus V, plus 3 volts. When Vi rises above plus 3, the diode turns on and locks the output at plus 3 volts. When Vi is below plus 3, the diode is off and Vo equals Vi. The output waveform matches variation 9. Again, the same clipping result from a different internal arrangement. Variations 9 and 12 both clip the positive peak at +3. Variations 10 and 11 both clip the negative peak at -3. The transition voltage and the clipping level are set by the battery direction. The diode orientation alone does not change the output shape here, because in the parallel biased clipper, the output locks at a fixed voltage when the diode is on. Let us put all four together. Every parallel biased clipper has one resistor in series and one diode plus one DC battery in the shunt branch. The battery sets the clipping level. Direction 1 places it at +V. Direction 2 places it at -V. When the diode is on, the output is locked at that level, like a voltage limiter. When the diode is off, the output follows the input. Variations 9 and 12 clip the positive peak at +V. Variations 10 and 11 clip the negative peak at -V. Compare this with the series biased clipper from lesson 6. In the series version, the output shifted by V when the diode was on and dropped to 0 when off. In the parallel version, the output locks at V when on and follows the input when off. One practical note: a real silicon diode shifts the clipping level by about 0.7 volts. For example, with a 3-volt battery, the transition moves to 3.7 or 2.3, depending on the diode orientation. Next lesson, we'll look at the double source clipper, which uses two diode branches to slice the waveform at two levels simultaneously. See you there!